Dear colleagues, today I want to present you our research cross-domain robustness of transformer-based key phrase generation. And I want to start with what is key phrase generation. I think every person in this room had to use some keywords or key phrases. And why do we use them? Because we need to create some search engine. We need to find scientific papers or some newspapers more effectively than just searching them by all words in the text or by their header. And what if we don't have any keywords? Then we can create them, evaluate them. And there are some classic approaches. First of all, basic TF-IDF, of course. Then if we add some more information, for example, a part of speeches, or maybe we will choose more words from the beginning, from the introduction of the article, it can be more effectively, according to some papers. And then we create a Yake algorithm. Then, if we have a rather big data set, we can train some simple classificator, for example, naive Bayes, on some simple text representation, and that is a key algorithm. Then we can use some semantic. We can create semantic clusters for words in the text and choose a representative from each important one. Then it's a topic rank algorithm, which was inspired by PageRank algorithm, which was used by Google to evaluate relevance of each page in the internet, in the Google index. So if we want to use some more modern text representations, we can take some BART and evaluate the text embedding, and then evaluate embedding for each phrase or word in the text, and then compare them with cosine similarity, and just took some most similar to the whole text. But all these approaches have one big issue. They are only extracting words from the text. But if we take some data set and check it, we can find then that in many cases, especially when we talk about articles and abstracts, more than 1/3 of the key phrases are not mentioned in the text. So the solution for this problem is text generating. We can take some sequence-to-sequence generator and create new key phrases which were not mentioned in the text. And in previous research, we found that BART algorithm can be very useful for this task. And its results are better than for classic approaches. But for classic approaches, we usually do not need any data set. Any tag data set. For Keyphrase or topic rank, we don't need any data set at all. But for this sequence-to-sequence approach, we need rather big data set to fine-tune our model. But for many domains and languages, we cannot do that. So the next question we wanted to solve is, could we transfer learning from big data set from one domain to another? For this research, we used 6 data sets from 3 domains, two scientific, computer science and biomedical, and one domain was newspapers. We used topic rank, Yake, and BART as baselines, and we fine-tuned BART base to compare it with the baselines. So, brief description of the data sets are on the slide. So they are rather different in size and in text characteristics. So here you can see the most popular key phrases mentioned in the data sets. And here we compare lexic from each data set using a method described in sketch engine corpora comparison. So another important question is which metric should we use? The most simple and I think most popular is F1 score. But in this case, we often find that model generates synonyms, which is not perfect matching, but for human, not for metric, it can be rather good. So we calculated 4 metrics: F1, Roach 1, Roach L, and BART score, which calculates semantics of original key phrases and generated key phrases and compare their cosine similarity. But there is no penalty on generated some synonyms in one sequence. Here's a simple metrics example. As you can see, original key phrases are ebooks, library journal, library automation, electronic books, and electronic publishing. And generated key phrases are ebook revolution, consumer market, reading devices, and electronic publishing. If we calculate F1 score or Roach 1 score, it will be below or about 1/4. But BART score is about 90%. And maybe for human, this score here is the best one. But this score does not allow us to create some penalty for generating synonyms, and it's rather complicated maybe to use general BART to compare embeddings from different domains, very specific domains. So in this research, our focus was on F1 score. I did not put all the results on the slide because they are rather big table, and the numbers will be really small. But we compared learning training on the target data set and training on each data set, testing on each data set. Then we mix them, mix all data sets in the domain and all the data sets at all. So, of course, on the target data set, when we train a model on the target data set and test it on this data set, the results are better than by baselines. Not for all data set, for DAC, which is a newspapers data set, but really small, the results of BART score were better. And if we try to use some out of corpus data set to train the model, the results are rather bad. and mix all strategy gave us the best results. Mix all is the strategy when we mix all texts in the train data sets and train our model on the whole big data set. So here are the results. There are results on target data set, on domain data sets. When we took only text from domain, in equal case, we took equal number of texts from each data set, and in all, we took all the train text. As you can see, kp times result on domain equal is rather bad. That's because DAC data set was really small, and there was not sufficient data. And mix equal mix all the same way, but we mix not only a text from domain, but also from every domain. And another interesting question is can we train our model on some data set, then fine tune it on few shot learning and get the better results than fine tuning it from scratch? The answer is yes, of course. And if unfortunately I don't have here the line for best baseline, but for 5 of 7 data sets, 7 because Krapivin data set was articles and texts, so we create 2 sub data sets. For 5 of 7 data sets, few shot learning of the model gave us better results than baseline. So that's the answer for the first one, the first question. Should we use some baseline on low resource language or specific domain, or should we train our model on the available data sets, available big data sets, and then few shot them on our specific domain? So our research will continue, and our final goal is to transfer learning from English, where we have a lot of text data sets, to Russian, and to not only to scientific articles, but also newspapers, and maybe integrate them into Russian national corpus. So thanks for your attention.
Thank you very much. So questions? So I can ask first question. What about Russian data sets? Do we have any data sets with keywords for Russian, something published?
I'm not sure if it's published, but in previous research, we've done 2 such data sets from MathNet and from Kiberlenenko. I think it's on Mendeley. And also this year we created, but it's certainly not published yet, data set for newspapers for needs of Russian national corpus. We added keyphrases there, and we tagged some data set. But as I know, as far as I know, there is a lack of Russian data sets in this field.
And what about this new newspaper data sets? From what is the source of keywords from these newspapers articles? did you generate keywords or extract it from some papers?
We extracted them from text and using root term extract algorithm, and then improved the tagging by human resources.
So we evaluated and corrected keyphrases using.
But now it's only a simple extracting approach. Our generating approach is has no good quality to use it in real applications yet.
Thank you. Questions? So no questions. Thank you very much for your presentation again.